Hello, in lesson 3.6, graphing logarithmic functions, you're going to learn here the identify key features of logarithmic functions. You'll also learn how to identify logarithmic functions using transformations and graph natural logarithmic functions transformations. Now let's look at a log. Now remember, a log function is the inverse of an exponential function. Therefore, to sketch the graph of y equals log base b of x, use the fact that the graph of the inverse function of these logs are reflections across the line y equals x of an exponential function. So for example, we have f of x equals b to the x power, which is this function here, this one right here. The domain is all real numbers. Your range is all of the values of y greater than 0. And it intercepts the y-axis at 0, 1. You have a horizontal isotope on the x-axis, and the end behaviors are as follow. As x approaches negative infinity, the function values are approaching again that horizontal isotope, so they're leveling off, approaching 0. As x approaches positive infinity, that end is pointing upwards and it's increasing without bound. So that's approaching positive infinity. Now, if we take the inverse of b to the x, that is log base b of x. So here, the graph of that will look like this. So it's a reflection of this line, of this curve here, across this line. And because of that, the log base b of x has the following properties. The domain, as you'll see, is all of the positive values of x, so from 0 to infinity. The range is now all real numbers, and again, that's just simply by understanding that inverses flip the domain and the range. The intercept, as a result, also switches to the x-axis at 1, 0, and the isotope is now a vertical isotope at x is equal to 0 at this line here. Oh, which I need to make a correction over here. I wrote x equals, I meant to write y equals. I did say horizontal line, y equals 0, but I wrote x equals. So this is the horizontal isotope for this blue one here, and this is the vertical isotope to log base b of x. Now, as a result, again, of it being a reflection across this line, a log function being a reflection of our exponential function, the end behaviors are as follow. As x approaches negative infinity, again, this graph is getting closer and closer to the vertical isotope, but again, it's unbounded. So it approaches negative infinity. And as x approaches positive infinity, again, this is increasing without bound. And it's going to approach positive infinity. So these are the end behaviors to this function here. Now, because all logarithmic functions, regardless of the base, behave something like this, they're all going to intersect specifically at 1, 0. Of course, the curvature changes it depending on what the base is, just like depending on what the base is here on this exponential, the curvature changes here. Now, some key characteristics, however, that are consistent regardless of the base is the transformations. It's specifically at that point, this y-intercept, along with everything else again, but this point right there can be noticeably shifted by the following transformations. Horizontal translations shifted to the left or to the right by doing the following operations. If I want to shift it vertically, I would add or subtract the value of k, and it would look like this. To reflect it across the x-axis, I would put a negative sign in the front, multiplying again the entire function by a negative. And if I want to flip it horizontally across the y-axis, I put a negative multiplied by my x value by a negative. Now, if I want to result in vertical shrinks, I multiply the function, the log base b of x, with a scalar of a that is greater than 0 if I'm going to stretch it, and a value between 0 and 1 if I'm going to shrink it. If I'm going to result in a horizontal dilation, I would multiply the x variable with that scalar. And if I want to stretch it, I multiply it by a value between 0 and 1, and shrink it will result in a value greater than 1. So let's now discuss the domain of these logarithmic functions. Now, the domain of a log function of the form f of x equals to log base b of x is a set of all positive real numbers, which again we discussed. We know again from what we graphed that the domain of this function here is going to be all of the positive values. So x has to be greater than 0. In general, the domain of a function log base b of g of x consists of all x values for which g of x is going to be greater than 0. So let's say we have a transformation, horizontal transformation along with some horizontal dilations. Well, we identify what the domain is by making this part, again, the value of the log greater than 0. So for example, say here we have a horizontal shift of the natural log of x plus 4. See how it directly correlates to this idea. Because this is the notation, if I go back to the previous slide, we're doing this. So it looks exactly like this, the log base b of x plus h. So that's going to shift it h units to the left. I'm sorry, I think it was minus. No, it was plus. So 4 units to the left. So this graph, let me draw the original graph. Normally looks like this. But because of the plus 4, we're going to shift this graph 4 units to the left. So let me grab this graph and shift it 1. And let me label this point with it right there. Let's shift this 1, 2, 3, 4. So the y-intercept, the x-intercept is now located at negative 3, 0. Instead of 1, 0, which again is a shift of 4 units to the left. The horizontal isotope has also moved 4 units to the left. Instead of being here at x is equal to 0, vertical isotope, I'm sorry, not horizontal, vertical isotope, this line has now moved 1, 2, 3, 4 units over. So that's the new location of that. So you see the graph has moved to this new location. Because of this, you can clearly see that the domain of this graph here is all of the values greater than negative 4. Which if we solve this equation here, or I'm sorry, this inequality, and I get to this portion here of x plus 4 and have it be greater than 0, the solution to this is that x has to be greater than negative 4 in order for x plus 4 to be greater than 0. And that again correlates exactly to what we see here in the graph, that this function only exists to the right of 1, 2, 3, 4, of negative 4. Now for a vertical shift, the vertical isotope does not change. It's still going to be in this location. Because if I was to move it vertically up, it's still going to be in the same location. Like right now, moving it up, you'll see it's same place. It goes up higher, but of course it's already going up because it's a line. Hence, again, the arrows. So that doesn't change. However, shifting again the graph 5 units is going to change particularly the x-coordinate and move the the x-intercept to a different location. So this point here that's at 1, 0 is now going to be moved up 1, 2, 3, 4, 5. And look at what the domain is. The domain is all of the values greater than 0. The graph exists to the right of this vertical line, which is at x equals 0. So, and that again directly correlates to this inequality, that x has to be greater than 0. And since it's already solved for, well, there's nothing again to do, no inequality to solve for, x is greater than 0, and that's exactly what the graph is indicating and showing us here. Okay, now to graph reflections, for this particular reflection, it's simply going to flip the graph upside down. So instead of starting down here and going up, it's going to start from up here and go down because of the vertical reflection, the negative sign being there. So let me first draw the vertical isotope, and then I'll draw our function. And again, it has to be a little bit more curved, but you get the idea. Okay, it will look like this. And here we have no horizontal or vertical shift, so we will be intercepting the x-axis at 1, 0 still. The graph is just simply upside down now. Now let's use this information on how the graphs again transform and the notation on the transformations of logarithmic functions to write the equation of a transformation of a log. Let's assume that this is the natural log. Here we have that's going to be a log of base e. So we want to transform g of x, which is just simply the natural log of x, and come up with the equation for this function here, f. Again, this function is f. Well, the easiest and most convenient way of figuring this out is by analyzing where the graph normally crosses the x-axis, okay, which is there, and comparing it to where it is on this graph right here. Well, since the vertical isotope is normally here at the x-axis, at the y-axis at x is equal to 0, we can see that this thing has been shifted. We have moved this to this location there. So it's at -4. And from there, identifying the vertical isotope, we can see that this point that the graph normally goes through at 1, 0 is now located here. So from this blue point to this new red point there, that is a shift of 1, 2, 3, 4 units to the left and 5 units down. So that would create the natural log of x minus -4, which is x plus 4, and then plus -5, so minus 5. And that is the equation to this function here. So as long as the graph is facing in that direction, we just simply are going to count again the position from 1, 0 to its new location. Now let's say the graph was facing the opposite direction. Well, because it's facing the opposite direction, we're not going to use again this graph here and count from this point to that point, because that would not be an accurate equivalency because the graph is pointing in the opposite direction. So instead of trying to compare this f of x, this function here, with the natural log of x, we want to compare it with the natural log of negative x, because natural log of negative x is going to flip this graph horizontally. And if it flips it horizontally, let's draw it in blue. That would make the graph look like this. Okay, so instead of counting from 1, 0 to this new location here, let me put it right here, we want to count from negative 1, 0 to this new location right there, because it's facing in the opposite direction. Well, let's count. That's going to move the graph 4 units to the right and 5 units up. So the equation to this would be the natural log of, we have a negative sign because it's pointing towards the left of the horizontal reflection, and negative x minus positive 4, and then plus, outside the parentheses, plus 5 to move it up 5 units. And while this again is acceptable, this is fine. Normally we see that we distribute this negative sign into and multiply x and negative 4 with the negative sign. We end up with negative x plus 4 plus 5. So that would be the function for this. So very basic rule of thumb. All we're simply going to do in order to figure out what the function for our natural logs are is simply count from the original intercept to the new location that has been moved to. And it's going to be negative 1, 0 if the graph is pointing to the left, so the natural log of negative x, and transform that. And if it's opening or pointing towards the right, it'll be the natural log of x. Again, the graph pointing in that direction. We want to transform this. And again, using this notation and understanding, okay, if I want to shift it to the left, I have to subtract that number. Well, I'm sorry, add that number. I want to shift it to the left, subtract it if I want to shift it to the right. And to move it up and down, I would add that value of k to move it up and subtract that value of k moving it down. And again, if it's upside down, I put a negative on the outside. And if it's pointing towards the left, I have that negative on the inside. And there you go. Okay. And you go back to that, to this one here. So you see, there you have it. Well, that concludes again the examples on graphing natural log equations and writing the equation to these natural logs given a graph. Well, again, thank you for watching. If you have any questions, please send me a message through email or remind. And like always, I appreciate you watching, and I hope you have a great day. Goodbye.